Dan Abbott, I'm making this video because Zoom failed to record our Zoom class meeting today. It's the first time that's happened to me, even though we have it set to automatically record. I have no idea what happened. It's simply no recording there. So I'm going to do a recap of what we did in class today. And I'm starting with our home page here. Home page has an offset section video. This video is one I made because we didn't have class Thanksgiving week. And this covers the approach that you need to take to the offset section drawing that is due next class. I expect you to watch this video and then do the drawing based on that. The assignments we have left, however, let's go to the assignments tab. There is a final exam review sheet that is open and has been open for some time, and that exam review sheet covers the same kind of material that will be on the final exam. In fact, it's an old final exam. So go and open that up, and when you come to class next week, I will answer any questions you have about the exam. Your responsibility to go and open this up and try it, see what kinds of problems you might have, and then bring those questions to class next time. I'll open the final exam the last week of the semester, which is coming right up, by the way. So the half section you've already done, the architectural full section you've already done, and the offset section for the caster is the one that is now due on the 5th, and that is the one I made the video for that you have to watch to determine how to make it. The week after that, which is the last week of the semester, you have a choice. I'm giving you 3 possible assignments, and it's up to you whether you want to do 1, 2, or 3 of them. One of them is an auxiliary view called a primary auxiliary view. The other is a secondary auxiliary view, and the third is a site plan or a civil plan. And I'm going to go over all 3 of these right now, and I want to make sure that you understand a little bit about each one, but it's your choice which of those you want to do. You should base this on the kind of discipline you're most interested in going into. 2 of them are mechanical, one of them is civil. But I started the class answering a question by one of the students, and the question had to do with this drawing. Now this was the full section elevation that he did, and I put a note on it when I evaluated it that he had no need to rotate his view 90 degrees, which he did because he wanted to put it on paper that was horizontal. And I probably should have mentioned this at some point, but not all drawings are horizontal. It's possible to have a vertical format for a drawing, and the vertical format would go in a sheet exactly the way that he put this one in here, but you don't need to rotate the view to do it. What I'm going to do is go back to his drawing. I'm going to rotate everything in the drawing, and I'll put it back to being upright. So this is the way you'd want to draw this, because this is the way you would be able to determine most easily what you need to put where. So if you have a drawing that's in a vertical format like this, you go to a layout. When you set up your view on the sheet of paper, go to Page Setup Manager, monochrome, of course, again for this class, DWG to PDF, and then when you select your paper size, and he was using B size, we'll do ANSI full bleed B 11 by 17. Simply go over here and instead of picking landscape, pick portrait. When you're done, drawing looks like this. Now you can bring a title block in, and you must have a title block in here. Let me see. Bring your title block in and put it in place. So there's an architectural title block. Now it's going to come in, I'll just stick it right here, fill in all the attributes. You rotate that title block 90 degrees, and then you put it on the sheet in a location that seems to work for you. You know, just kind of center it on the sheet. Then you can put your viewport in here accordingly and give yourself as much room as possible. Now just zoom in as far as you can go. The reason for doing this vertically like this is you can use a lot more of the white space on a sheet of paper because the drawing itself is a vertical format. So come like over here, pick a scale that you think is going to work for this. Let's go with 1/4 inch. I think 1/4 inch is probably as good as we're going to get on this one. So you rotate it to a 1/4 inch scale, in this case a 1/4 inch scale, lock the viewport, and now you work from here. Now when it comes to filling out the title block, you go ahead and do that. We could have filled out the title block before we rotated it, or you can just fill it out by rotating it. When you have attributes, it's kind of nice because if you double click on this, it opens up the attribute dialog box, and you can just fill things in the way you would have when it first came in. You don't have to worry about tilting your head. There was one other question that came up that I think would be helpful for you to see the answer to. So let's go back to the assignments. And for this one, let's go and look at the offset section assignment. The offset section assignment is this caster file. And this caster is a mechanical part in assembly. And what you need to do is set it up so it looks like this. And I had brought in fact, on the video I showed you, I have a 3D model of this. I showed you how the cut would take place. I made it clear that the cut in this particular case is really a full section, but it's actually offset because the part itself has the fasteners in such a place that they're not in the same plane as the center of the part. As long as I'm doing this now, let me just open that up. I'll show you what I mean. So here's a drawing done by one of the students in the parametric modeling class of the entire assembly. And a couple things to point out. There are very few dimensions on this. You don't try to dimension all the individual parts. Instead, when you have an assembly like this, you draw the parts individually using orthographic projection the way you would anything else. So the parts for this would be drawn by themselves. The assembly is simply to show how everything goes together. If you take a look up here, this is the cutting plane line that she used to set up this full section assembly. And the reason it's offset is so that you can see how the fasteners appear in here, as well as going right down the middle, how the axle and the wheel and everything else would look as well if you cut down through it. Now when you do a full section assembly of or a section of an assembly, you don't cut through the fasteners because it would be much harder to read. So that hex-headed bolt, the washer, and the nut, those are drawn as though they weren't sectioned. Same with a shaft that is shown like this longitudinally. Now I've modified this a little bit because I'm going to make a point in just a minute. Let me just open this up and show you what I mean by that. This is what it really looks like. So if we really were to cut it right down the middle, so it looked like that, that cut would not go through the fasteners. So if we then looked at it from the front, you wouldn't see those fasteners at all. It would also, if you just did a cut through everything, it would cut through the shaft, and that just doesn't look right. If I did cut through the bolts, that would also not look right. Back that up so it does that. Because you would be showing the bolts in section as opposed to what they look like, which would make it hard to tell that they're hexagonal. You know, you'd just be cutting down through here like that. That didn't quite go through the middle of the part. So anyway, this is why you do an offset section. Now if we go back over here, the question that somebody asked was, do all those angles have to be different? And the answer to that is yes. All these angles have to be different angles. And this is and when she did this in this class, she did it correctly. This is a weird little glitch in SolidWorks. It has nothing to do with AutoCAD, but it is CAD software. It happens all the time. CAD software now has a subscription basis. Every year they update the software. Every year it introduces some new problem. I'm going to try to fix this with this weird walk around, which is to delete that view. And once I've deleted that view, I'm now going to bring it back. And normally when I bring it back, it comes back and everything is fixed. But in this case, it didn't. So all those section lines have come in incorrectly. Let me go back to the handout. And in the handout, the angles on all these section symbols is correct. So if you'll notice on this one, and again, the reason that hers did not have that was because of a glitch in SolidWorks. So you take a look at this. In the first place, you use different symbols for different materials. So that top one is steel. Those double lines with a gap in between are how you designate steel. The angle on that and the angle on this are not the same angle, and they're off by 15 degrees because the angles you use have to differ by 15 degrees at least. So you notice this angle right here, a little bit, is 15 degrees greater than that, which is 45. This is also 45. No, this is 45 over here. That's 45 over here, which is okay. And the reason that's okay is because they're two different symbols. Over here you have the same system, same symbol, and it's at an angle that is 90 degrees since it's a mirrored part. If you have identical symbols and angles on two different surfaces, that means those surfaces are connected in a single part. This is the wheel and the caster. When you cut down through it, that's the top part of the wheel, that's the bottom. So that and that have to have a hatch pattern or section lines at the same angle. That's a different angle, that's a different angle, that's a different angle. And then down here we have 45 degrees and 45 degrees, but the symbol itself is for bronze because it has the dashed line in the middle, which means it's a copper-based system. The other thing is this top plate is just how the caster is going to be bolted to something. That top plate isn't part of the assembly itself, so it's shown in phantom lines, and the phantom lines are the two little short breaks. Now we're back to the last assignment with the three different possibilities. First possibility is a primary auxiliary view. Primary auxiliary view, we'll open that up in Adobe. Hang on just a second. So the first one you can do looks like this. Let's rotate that way. And this is known as a primary auxiliary view. There are two primary auxiliary views here. And this is a situation where whenever you have a surface that is not parallel to one of the 6 primary planes used for orthographic projection, you're still going to project orthographically, but you're going to project directly from the surface that's at that angle so that the view you show is 90 degrees to the surface you want to represent, but it doesn't show up in the correct size or shape in the right side view in this case, or a left side view. And then the top view in this case has a short break line. It's called a partial top view because these wings that come up would also not be shown in true shape. Now to demonstrate that, I'm going to use a SolidWorks model. But first, let's take something simple. This is a cylinder, and it's got a surface that's been cut off at a 45-degree angle. If you look at it from the front, it looks like this. Look at it from the top, however, it looks like that. That surface looks like a cylinder because when you project it straight up with a 45-degree cut, it looks round. Look at it from the right, it is a cylinder. Looking at it from the top, it appears to be circular, but you look at it at the front, you can see that that surface is much longer. So if I looked at it really directly at it, that surface we're looking at is actually an elliptical shape. If I wanted to show that elliptical shape in its true shape and size, I can't do it from the top, and I can't do it from the right. So what would I do? I would create what's called an auxiliary view, and this would be a primary auxiliary view. Auxiliary view in this case would look like this. Where we have a front view. I could put a top view in here just to show that that's a circular feature when it comes up. But this is in SolidWorks. This is generated directly from the part itself. That's the surface, and I would place a view of it right here called the primary auxiliary view. And you can see that because of that 45-degree angle, this length right here is obviously greater than this length. So the width of the ellipse is the same as the diameter of the hole, but the length of the ellipse is based on this angled cut. You project lines at 90 degrees that go up. You can see the ellipse here is 35.35 millimeters, whereas the diameter is 25, so it's 25 here and 35 there. That's a very simple primary auxiliary view. The part you have to draw looks like this, and you can see those wings going at various angles. So you can draw this in true shape in the front, because in true shape in the front, those angles are projected and you can see what the actual angle is. If, however, you went to the top view in this case, that's distorted, Those look elliptical. The sides get a little bit closer together. That shape looks okay, except it's not true because it's at an angle. So when it gets projected up, you get something called foreshortening. So what do we do on this one? On this one, you're going to do the same thing I did on that cylinder. You're going to project views so you can see what the true shape looks like. Now yours are going to have fully dimensioned, etc. But right now, this is what this would look like if I were to cut down through this. And then in this particular case is a similar situation where if I cut all the way through this, straight through it, what I would end up with here, is no holes would be shown here. So those holes by convention are shown as though the cut went through the holes and through the middle of the part. The part that gets cut has section lines. The rest of it shows object lines where they would otherwise be hidden lines. This gets projected at 90 degrees, 90 degrees. Over here, 90 degrees, 90 degrees. So you see the true shape of this, the true shape of this. And then you actually cut this off so that you don't show and don't have to spend the time drawing the distorted view of this. Now, this is SolidWorks, so if I wanted to show that, I could. It would look like that. But it doesn't help me any because that's nothing. None of those things is true shape. I couldn't put dimensions on here. So for instance, if I tried to dimension that right there, it's going to tell me the true radius of it because it sees it as arcs as opposed to a circle, or as opposed to down here, you put something on there and it can actually put in what the dimension is. So I'm just going to give you some an approach to how to do this, but I'm not going to draw the whole thing. You know enough about AutoCAD at this point, so you don't need me to. The key thing here is to use the offset command. So there are two things I need to show you here about this. Hang on. Two things I need to show you. One is, well, two things I will show you. One is I want to show you how you can easily create auxiliary views that are primary just by drawing in the shape that's in true shape first and then using offset to draw the rest of the view. So if I come over here, I'm going to draw a rectangle for that middle part. Rectangle 76 by 25. So that's the center part of this. Now if I go ahead and over here, I draw line coming out. Actually, I don't know exactly how far that comes out, so I'm going to offset this 12. Offset's a very helpful command in all of this. Now what I want is for this line right here to be 20. I'm going to show you a command called lengthen. Lengthen allows me to say I want to know the total length of this has to be 20. I pick it here and it shortens it down so it is 20. Now I'm going to go back over here and I'm going to draw this at an angle of 30. I don't have 30 set for polar tracking, so I'm going to go and set it for polar tracking. So this comes up like that. It's going to be 76. Then that's going to come up in a 90-degree angle. That's going to be 12. Then this is going to come down. Don't acquire that point right there. It's going to come down at an angle of 30, so it'll look like this. And then if you fill it by holding the shift key down, those two corners, that's going to give you what you want here. Now, in order to create the auxiliary view, I'm going to offset some distance. Bring that down here like this. Offset the width of the view, and the width of the view is 50. Bring that down. Now when I connect the dots end to end, that is the true shape of this. At least it will be once I put in those little fillets right there. What are they supposed to be? Oh, 5. Fillet radius of 5. Didn't look quite right. And then you go ahead and put the circles in. Once you do that, I won't bother to draw exactly where they go, but once you do that, you can then project up from here 30 degrees to show where the circles go. Now you can't, although I will say you can't do it from the quadrant because the quadrant hangs down here. So here's a case where you're probably better off, what is that, 12? I would come up here and I'd offset 12, go to the center line on this, offset that 12, and then if you know that the holes are 14, you can offset 7 going back, and then just get rid of this. And now what that would line up with would be the hole down here. So the hole down there is going to be 12 in from here and 12 in from here. Not the real way I would draw that, but just so you can see what I'm doing. I do this, diameter is 14, the hole looks like so. Get that out of there, get this out of here. Now if we were to project down from here directly at the 30 degrees, it's going to go right through that hole. Two other things that I want to show you. One is, what do you do about this little squiggly line up here? So that squiggly line up there is the result of having two lines that come out, and they come out beyond that. And the reason why it's significant is because the true shape in the top view, looking straight down, the true shape is going to be that surface right there, which will show up here as a hidden line. So you want to make sure that you have enough of this there to show that hidden line. Now you go up here, and there are two ways to put that short break line in. I actually like P-line as a way to do this. So you just kind of draw something that's got a little bit of jaggedness to it. When you're done, you use the P-edit command, and you P-edit that, and then spline fit it. And now it has this kind of rough look to it. There is a spline command you could also use. When you do the spline command, you just kind of do this. But splines tend to look way too regular. They look a little too smooth. So no matter what you do with it, it doesn't, to me, look quite what it should look. Either one of them is okay, as long as it's not a straight line that makes it look like that's the edge of the part. So you're going to have to do all this, put all the dimensions on here, put your cutting, your section lines in, and you know, you're going to use the dimension style you created for mechanical metric. And the only other thing is, and I'm not going to show you how to do it, but this little symbol right here is a finish symbol. It's actually a little too small. It should be 3 times the text height according to the ASME standard. That really gets in the way from my point of view. So I tend to make mine smaller. But all you have to do on that one is make a block out of it, draw 3 lines. It's a 30-degree angle and a 30-degree angle. And then just insert that block in the locations where it shows. Otherwise, duplicate what's there. Don't put the text in, but duplicate what's there. And it does give you some instructions up here. Yeah, that's, I think, everything. Oh, there is one other thing over here I want to show you. You've got a situation over here that comes up where people often use the wrong dimension style. And that's that dimension of 76 and 45 right here. So let me go and create that rectangle shape. Well, I'm going to pause a moment. So we've got the wing on the other side that comes down like this, and once again I would offset enough, leave enough room for your dimension. We'll use offset again to get the width of this. Now what I'm going to do is put a shape on here that causes people some difficulty when they try to dimension. So if we have a line here that goes right up at 30 degrees and goes in 45 millimeters, and I offset that 10, which is the radius of the arc on the end, and I'm going to fill it 2 parallel lines, which automatically does that. Get rid of this, and then I'm going to put a fillet with a radius of 12 on this corner and on this corner. Now the question is, how do you put your dimension on here? I didn't set up a dimension style here, and I certainly don't want standard. I also don't want annotative. Well, I'm just going to modify that quickly and just make it decimal and then get rid of trailing zeros. All right. So people often think they're going to use the aligned command to put this dimension in here, but you'll notice something about that. When it comes in, never set it current. If I use the align dimension, so dim aligned, and I go from here to here, it's going to give me the distance directly between the two. Yeah. I'm going to make this annotative because standard is not a metric style. Well, you know that, of course. What I'm actually going to do is just to force it. That's really bad practice, what I'm about to do. So what I'm going to do instead is go up here and use the annotative style that is set up for metric and just fix it so it comes out right, which means it's going to be horizontal, it's going to be centered, and it's not going to use a comma, it's going to use a period. Trailing zeros will be suppressed. Okay, we'll make that our current style. Now, I'll come in here and I'll put in the dimension. So what I'm saying is the dimension aligned, when you put it on a situation like this, it's skewed. It doesn't give me the right number because it goes directly between the 2 points. So people sometimes have difficulty with a dimension like this. This is easily done though with the dim linear command, the same command you've been using for horizontal and vertical dimensions. If I go here and I bring that up, that's not correct, that's not correct, but I have an option up here for rotated. If I say let's rotate that dimension and I type in 30 degrees, now it'll come in rotated and give me exactly the dimension I want. Because of that arc, you don't get the gap that I want, so I'm going to grab this and then I take that end and I bring it out a little bit. Now there's a visible gap on it. If you don't know what the angle is, and that sometimes happens, if I take this whole thing, I'm going to move it up here, and I'm just going to rotate it to a random angle. No, I don't want the toolbars. I'm going to rotate it to a random angle by just doing that. Okay, now that rotated with it, which is what you'd want, I go back into a linear dimension, and if I hadn't put that dimension on already, and I say I want the dimension from here to here, and I want it to go to that end point right there. Again, it's a linear dimension, so it looks like it wants to go vertically or horizontally. If I go to rotate now, and I don't know the angle, all I have to do is pick 2 points at that angle. Now it's going to come in, and it's going to give me the same dimension. That's enough on this one. The rest of it I think you can do on your own without any difficulty. Now the other one that you have as an option is a secondary auxiliary. And a secondary auxiliary is a situation where you have a surface that's at an angle to more than one of the planes that are standard 6 planes in orthographic projection. We have 3 examples of that here. And each one of these has a surface that's angled in 2 different planes. This one has 1. Over here you've got actually a projection that is a primary auxiliary. Then you have a primary auxiliary, and then projected from that you would have a secondary auxiliary. Same thing over here. Primary auxiliary, and then from that auxiliary drawing you project another one. You can have tertiary auxiliary drawings for that point matter, although I've never seen one actually used. This one right here, I'm giving you some examples of how to set it up. It shows you the layout over here. But if you take a look, the process of creating this, and I'm going to go through this, I'll go through that with this one. The process of creating that is to start by drawing what you know. You're going to start by drawing the base. You don't need to draw all these distorted views. All you need is the stuff that you can draw in true shape. The base, the top view, this you don't even have to draw that whole thing in. And then you're going to project, once you've done that, an auxiliary view. Let me go and make a look at the 3D model so you can see what I'm talking about more readily. Alright, we've got another model here. Well, this one is going to be that. Alright, so here's the model that I just showed you, and you can see if you look at it, that part that raises up out of there is sitting at an angle in the base. And then the part itself also has an angle. So look at that from the front, distorted. Looking at it from the right hand side, distorted. Looking at it from the top, that shape that hexagonal shape also distorted. What is true shape here is the base of the part that's sitting on top of the other base. So what we need is to be able to show this surface right there in true shape. And then once we show that surface in true shape, we need to be able to look straight at that surface and see the hexagon in its true shape. Now, in order to do that, we're going to create an auxiliary view of this and a secondary auxiliary view of that. And the way it would look, and then we'll lay it out in AutoCAD, the way it would look and do the drawing would be like this. So you draw the base in because you know what the dimensions of that base are. The rest of this you can cut off because it's not useful. Then you draw the top view, draw this surface, which is the rectangle that's sitting there, and you have all the dimensions for that. And then the idea here is, what does it look like on that surface right there? Again, standard orthographic projection. If this were your top view of a part, you would draw it horizontally and then project directly to the right what it looks like here. So if we take that and project it 90 degrees, those projection lines are 90 degrees to that surface. You just bring that out here, all those lines get projected up. Once you have the basic shape here, you go ahead and draw that surface shape, which you know is correct. Then that surface is the one we want to look straight at because that's the one that has a hexagonal hole in it. Project that down in order to get the true shape of the hexagonal hole. So let's set this up and lay it out in AutoCAD. And again, you do have to put all the dimensions on here. I'm not worrying about that for this presentation because you've done so much of that, you should know how to do it. Well, you do know how to do it. So the process of laying this out, I would start with the front view, but I'm only going to draw the base. So I'll draw a rectangle, wherever you want to draw it. It's 4.7 inches long and 0.4 inches high. So there's my base right there. Now I'm going to draw the top of this, the top of the base, and I'll draw a rectangle that projected directly above this. Leave enough space for your dimensions at 4.7 comma 2.76. That's what it looks like on the top. Now you can see that that corner right there is 1.38 inches away from the center of that hole, plus another 6, so 1.98. So I'm going to draw a line starting, and I'll acquire that point, go to the right, 1.98. I'm going to draw that up at 30 degrees. And the length of that is given on the drawing as 2.4. Then I'm going to make a turn. Now having 30 set as your polar tracking angle and then tracking all polar settings allows me to draw this with tracking lines, including the 90 degrees. So that's going to be 1.4. This comes down also 2.4. And I'll close it up, looks like that. So that's the base here of what we're drawing. We don't have to draw the rest right now. What we don't want right now, and you can see there's a setup given over here. We want to draw this end right here. This end is the opposite end from this one. We could go down. You know, you could draw this down here. It's just probably won't fit on the sheet quite as well. So instead I'm going to draw it up here. Now it gives you some dimensions here for spacing. Those aren't required. Those are just sufficient to leave enough room for your dimensions. So if I offset 2.75, and offset's really a great tool for doing this. That gives me the top of this surface right here. So I want another line showing the bottom of it. It's 2 inches tall. I'm going to offset that 2 inches. So again, I'm drawing the height right now. That's the 2 inches. But I'm doing it projected directly off the surface that it shows in true shape. Now that I've done this, I can close up the back. Looks like that. Oop, doesn't quite look like that, does it? Goes to the end of this line. There we go. And now this little piece right here, this is the top, and you can see the orientation over here. That little piece is the top, and it goes 0.50. So again, I can use the lengthen command, just kind of like it, 0.5, and then I pick the end I want to get rid of, back to here. Now it also, yeah, you can see there's an angle given here, and the angle given here between that surface coming down and the top is 60 degrees. So if I go here, in other words, from here I want to go down 60 degrees. So I'm going to snap to this one and snap to that one. That's going to give me the 60 degrees. In this particular case, I'm going to just go beyond where I need to go, because I also need to start here and come back like this, also at 30 degrees. I'm just doing that because I wanted to make sure those are both 30 degrees. Now if I do a fillet, hold the shift key down, looks like that. So what I have now is that shape right there projected off of the back of this. Let's go back to this one. And you notice it looks just like the one I have here, and this one came directly from the model. And if I open the model, what I've done is said, let's take a look at the top of it. Now what we need to do is project that directly up. When we do it, we're going to get a shape that looks like this, so that now we can project that directly down, and what we're ultimately going to see is that shape right there, without the line in the back, because we don't need to show that. So that's where we're headed with this AutoCAD drawing. And you're going to do this obviously not from the model. You're not going to let the software do it. You're going to do it yourself. Right now, what do we do after that? After that, you just put this shape in here. If you look from the top, okay, 0.3 down. So we'll draw a line. And again, use your polar tracking. We'll draw it down like that, 0.3. Now this is an angle. It's a dovetail. Goes back that far, like that. And do we know? We don't know how long that is. That's all right. We do know the depth is 0.25. So we'll use offset again, 0.25. Bring that down here. There we go. Now once again, I'm going to fillet those two together. So that's the shape we have there. On the other end, we have a space. See overall length. Oh, 1.2. So from here, it goes down 1.2 and then comes back. We'll trim that out. Now I'm going to draw a line from here. I'm going to get the 1.2. Now the 1.2 represents that edge right here. So that's the bottom of the edge. Now I can go up here at the same dovetail angle like that. Fillet those two together to clean it up. And then just put a little line. It goes from here to here. That's the shape I'm after right there. And again, if you look back at the SolidWorks, model on this one, and then we look at the drawing that was created from it. We started with the top view. We rotated it down so we could see that view right there. That's what we just finished shaping, this whole thing right here. And now we need to project down to get this. There's the surface we're projecting down. That's the one that's going to give us our secondary auxiliary view. It tells you to go down, well, 2 inches from the front surface, so we can do that. And here's because of 30 degrees, this thing now ends up being a horizontal line. That's kind of helpful that it did that. But it's 0.25, so I'm going to offset this 2.25 because that again will give me enough room for what I want here. Then I'm going to offset, and again, what do we have here? It's the length. It's this distance from here to here, and that is 2.4. So we'll offset 2.4, bring this down here, and now we can go ahead and draw this in like that. Draw this in like that. Now you just have to locate the hex. Now that hex is 0.7 from that corner right there. So I'm going to draw a line starting here that comes down 0.7. I'm going to draw that line all the way up through. That represents the point of the hexagon. And the reason that's helpful to me is now it's going to have to line right up on where the hexagon goes here. Now the other thing is, where does it go from the surface? And the center of that is 1.2 back from here, so it's dead center on this. So what I'm going to do is draw a polygon. I'm going to take and draw the polygon by projecting it from, I need six of it. The center of it, I'm going to project this down from here. The midpoint here, that's where the hex goes right there. Now, it's given as the distance across the flats is 0.75. That means we need a diameter of 0.75 to circumscribe it. So I'm going to put this around. It's going to be in the outside of the circle. And it asks for the radius. 0.75 divided by 2 is 0.375. So that's what you have to type in there. If I look at this, though, it's not oriented correctly. I'm going to rotate it. I'm going to rotate it around its center. I can find the center in a couple of ways. Shift right click midway between 2 points from here to here. I'm going to rotate it 90 degrees. That's the orientation that it's in, because again, it's the long distance is where those points are. That point right there would now be a hidden line. We project each of these corners up, and those are the other 2 hidden lines. And those are those two hidden lines representing where the hex would go through. So those you'd put on a hidden line layer, and that is it. You can then project back to get some of the other lines, on here. And if you wanted to, you could even project those corners down here and then literally take a hex like this and then figure out the distances, and you could end up drawing it in what it looks like on the top view. However, you don't have to do that. You can, for my purposes, you can leave this way. People who understand what these drawings look like and what they represent would realize that you're projecting this off of there, you're projecting this off of here. Primary is the first one, secondary is the second. You don't have to do this one, by the way. You have a choice over here. There are 2 others that you could use as well. And if I were to open those up and just show you what they look like, nope, SolidWorks is what I want. That's the one we just did. Open up a couple more. This is the one that has a tab that comes out, but it's also bent down. This one, once again, you've got to set this up so you can see the front view. That's going to be the true shape here of the front view. And you know what the width of this is, but you only know the width from that orientation. So the only thing you can draw on the front view on this one is that line right there. Then you go straight off that line. That's going to project looking down 90 degrees. There is no surface that you can go 90 degrees from, so you're going to have to extend that line. Once you extend that line, you can draw that shape right there. And once you've got that shape right there, you can project it to get that shape right here. And if we go and take a look at what the drawing on that would look like. That would look like this. So you'd start with your front view. You project up, and that's going to give you the base of this. That's going to give you that corner right there. The height is given as a dimension. Once you get that height, that shows you that full shape. Then you take that surface, project it over to this. Now you're not going to bother to draw this. You're going to only draw that surface right there. I leave these on here just so you can kind of get a sense of what the whole part is doing as it rotates around. So there's your primary and there's your secondary auxiliary. On this side, the end of this has that slot cut in it. That's simply a primary auxiliary drawing. Let's look at the other one. And the other one that you can do if you choose to is this one right here. Nope, that's the same one I just opened. So it must be... Yeah, the other one's going to look like this. And it's also a primary and a secondary. So the front view looks like that. Again, that's distorted. The top view, though, you can draw that shape right there. That's all the dimensions are given that you need. Once you have that shape, that becomes the surface you want to use to project. You project that up. Offsetting that's going to give you the base. Everything else you project up is going to give you that corner. It's going to give you this corner. Once you have that, all you have to do then is bring that out, whatever length is given, offset this down, that width, and now you can project straight down to get the hexagon in that one. Up to you which one of these you choose. Now, there's one other thing I covered in the class, and that's how to approach the civil drawing. So the civil drawing, we can just close SolidWorks altogether since we're not doing anything mechanical anymore. All right, the civil drawing looks like this. This is a site plan. It's a very simple site plan, and it requires that a site plan is just a lot. So you're going to start at A, you're going to go around. A couple things to recognize here. When surveyors do a site plan, they have a starting point. They go through a series of turning points. All of the distances used in the United States are decimal feet. No inches, no fractions, no feet and inches. Everything is just decimal feet. 2 decimal places or sometimes 3 are going to be used for the survey. So the lengths of all these property lines are given as 110.00 feet. The angle is never given between 2 lines on a piece of property. It's always given relative to north or south. So what this angle means is that if we started at A and went straight up, that would be north on a map. If when we took that line that went straight up, we rotated it to the left, 24 degrees, 48 minutes, 18 seconds, and we go to the left because the left is west. So this line says go north, then west a certain amount, and that's the property line. Everything is given based on the ground, on a map, north being up. This next one starts off being north, going straight up. This time it goes east, 50 degrees, 16 minutes, 49 seconds. Now, the way that surveyors use angles always is always is degrees, minutes, and seconds. There are 60 minutes in 1 degree. There are 60 seconds in 1 minute. So you could convert those to decimal degrees, and you could do that and then draw with AutoCAD if you wanted to, and then bring them back. You'd have to go through, though, and convert every single angle in the drawing. So there's an easier way to do that. And the easier way to do that is to use surveyor's units when you draw. The other thing I'll point out is this. Always use all the numbers given, because surveys never perfectly close. There's always some error, and the amount of error determines the quality of the survey. But surveyors are on the ground with their surveying instruments and doing the best they can with some trigonometry to go around and describe a piece of property completely. But there's some variation, and so when you're done with this, there's going to be a little gap here. And the first question you have to answer in this one I think is a little easier to draw, but you do have to answer some questions. The size of the gap. If you close this up or snap back to the end point of that line thinking that's what it is, you're never going to be able to answer that question, because one of those 4 numbers is the size of the gap you have when you do a distance directly between the 2 endpoints. So the other thing that you have to take into account is when you plot it. So we're going to go through that process of setting it up for plotting. So here's AutoCAD. We're going to start a new drawing. Now, even though it's in feet and not inches, we're still going to start with an imperial. Bring that over a little bit. We're still going to start with the imperial template. So we go to a new drawing, take the ACAD DWT, but I'm going to make a few changes in units. One change I would make is to set it from inches to feet if I thought I might be inserting something that was drawn like an architectural drawing in architectural units. One weird thing that happens here, and civil engineers and architects often have a little conflict over this. If you're drawing in decimal feet, your unit in AutoCAD is 1 foot. If you're drawing in architectural units, the unit is 1 inch. As a result, I've had a number of cases where I've had to clarify for people, mostly architects, when they have an architectural drawing they did in AutoCAD and they try to bring it into a site plan, and then the drawing in architectural drawing 12 times too big. It's bigger than the lot sometimes. So if you have a situation where you want to combine two different kinds of units, you must set these units to feet before you bring that other one in, or scale it down 12 once it does come in. The key thing here, though, is not units of length. It's the way angles are used, and you need surveyor's angles in order to submit them in that way. North, 0 degrees, 0 minutes, 0 seconds. East, that's what it displays as a little symbol. Don't pick clockwise, whatever you do, because once you do this, it takes into account that north is up. Now we're going to stop and say OK. Now I'm going to draw, starting at A, because I put the A here because that's where the gap takes place. So this is where the surveyor would have started. And you're going to go up around here like this. And again, just to kind of make the point, if I started a line from A that went straight up, and then I rotated it 24, well, let's just say 24 point, like 0.7 degrees, you can see it would be close to that angle. I just estimated what that would be. And by the way you would do it for real is you say, what is 18 seconds divided by 60 seconds, we'll do that, per minute. And when you get that value, you'd add it to the minutes, and then you would take whatever you got there and you'd add that to the degrees. That would give you a decimal degree. But again, in civil plans, you never use decimal degrees. So the only reason to do that is because you have to do something in AutoCAD and don't know how to use the surveying units. So now let me get rid of that. So what I'm going to do is draw a polyline. I'm going to start it someplace, and I want to go off in this direction, but a polar tracking is not going to help me any because there's no way I'm going to set this to 1 second of an angle. So instead, I'm going to use coordinate entry. Start with the @ symbol, meaning that I'm starting this line at the last point I entered. I'm going to go the 110, that's the distance. Do not put a foot mark in here because we're using decimal units. Doesn't understand the difference between feet and anything else. Less than, which means at an angle of. North, 24. Now I go, wait a minute, I don't have a degree symbol on my keyboard. And because there's no degree symbol on the keyboard, Autodesk picked a letter to designate degrees, and it'll be no surprise to know that letter is the letter D. So 24D, 48 minutes, an apostrophe, 18 seconds, quotation mark, west, and it goes at that angle in that distance. Now the next one, at, starting from the last point entered, 83.33 feet, don't put the foot mark, at an angle of north, 50, the letter D standing for degrees, 16 minutes, 49 seconds. In this case, east goes like that. At 93.44, at an angle of south, 37 degrees, 35 minutes, 18 seconds. East, let me look and make sure I did that correctly. Yep. At 81.45 at an angle of south, 14D, 34 minutes, 23 seconds, west. Comes down like that. And here's where a lot of people just go and snap to the end of this and think that looks good. But you notice that's the angle, and that's the bearing, and that's the property line distance. So another at symbol, 54.43 at an angle of south, 89 degrees, 45 seconds, 31 minutes west. Now that looks like it connected, but when you zoom in on it, you'll see it didn't connect at all. There's a little gap there. Small enough gap, and it's a very, very high quality survey. But you need to measure the distance from here to here, not the horizontal distance or the vertical distance, but the direct distance between those two. So I'm going to show you what I mean by that. But first I'm going to move this, so this will not be the correct answer. Use the dist command, go from here to here. I'm going to undo that. Now, that gives you the basic plan. Now you can also put this in with no difficulty at all. So once you get that basic plan though, I want to show you a technique for putting dimensions on it. And the technique for putting dimensions on here is going to involve creating a special dimension style for civil. So I go to the dimension style. I want it to be annotative, so I'll pick the annotative style. I'll set it current. I'll rename it. So it says civil instead of annotative. Now I'll go down and just delete standard. Come back over here, modify. I'm going to go and modify this by doing the following. See, the dimension is just the number of feet over the property line, which is already there. No dimension lines with arrowheads, no extension lines. That's just the way it's done. So if we go to lines, we can say let's suppress dimension line 1 and 2, extension line 1 and 2. Excellent. The other thing is the dimension is above that line and it lines right up with the property line. So go over to text. We say instead of horizontal, have it line right up. Instead of being centered, put it above. Then we go to primary units, and we don't want any zeros. Yeah, actually we're fine. Let's go to 2 decimal places. 2 decimal places. And then we don't happen to have any zeros here in the overall lengths. Oh yeah, we do right there. So we want to see those 2 zeros. So we'll use 2 decimal places of precision instead of saying get rid of trailing zeros. And the only other thing is, even though you don't put the foot mark in when you dimension it, when you draw it, we want the foot mark on the drawing itself. That's a suffix, comes after as opposed to a prefix. I'm going to just put, you can put anything you want here, by the way, REF or reference or anything else. I'm going to put the apostrophe in there so it comes in with the little foot mark on it. And then do this. Now that's all I need for that. I'm going to close that out. And when I do the dimensioning, this is the annotative now, I'm going to do it only after setting up a layout. So I go to a layout, and I'm not going to bother to go through and set up a sheet for you, but I do want to point something out. Your scales in civil are always in the format of 1 inch on the drawing represents some number of feet on the ground. So 1 inch equals 20 feet would be a civil scale. It means anything you measure on the drawing that measures 1 inch is actually 20 feet on the ground. So down here, you'd measure that line. That line would be, at that scale, would measure 2.5 inches or so, a little more than 2 3/4 inches. And that would be close to 54. So that would be if you could do a 1 inch equals 20 foot scale. The actual plot scale here then would be 1 to 20 times 12, or 240, and that makes sense. The land we're drawing is 240 times larger. This is where people get confused. What I want you to recognize here is this. The plot scale and the viewport scale are only the same if the units in model space and the units in paper space are the same units. So in other words, if you draw something in inches and you plot it on a sheet of paper measured in inches, whatever you get for a viewport scale will be the actual plot scale. If, however, you draw in units that are different from inches, then whatever you have for a viewport scale is a ratio where the number on the left is the sheet of paper, the number on the right is the units you used on model space. Now if I go and open this viewport up and I come down and go looking for something, if I were to do something like, well, let's just try an architectural scale, which is never used for civil, well, that's pretty small. The actual scale I'm going to try now is 1 to 20. Well, 1 to 20 would fit if I made my viewport a little bigger. This is on an A-size sheet of paper now. Now you know 1 to 20 can't be the actual plot scale because the land must be more than 20 times larger than this one A-size sheet of paper. Has to be bigger than that. So why did this come out 1 to 20? because the units we use to draw are feet and the units we use to plot are inches. So the VP scale is 1 to 20. The 1 is 1 inch and the 20 is 20 feet, which, by the way, is exactly the way you would then write 1 inch equals 20 feet, a civil scale. So that's the viewport scale. The plot scale would be 1 to 240. In other words, the land is 240 times bigger. But because you drew in feet, the number on the right is feet, you've got to convert the same units on both sides to determine what the actual plot scale is. Luckily, once you come up with 1 to 20, now you know that the actual plot scale is 1 inch equals 20 feet, and that's how you would write it in the title block if you're doing civil engineering. And you've all taken print reading. You remember we went over those scales. We went over civil, and that is the format for scales in civil. Now, let me just get rid of that. So now we're going in and we're going to put some dimensions on here. Open it up. Lock it. I know it's 1 to 20. I'm dimensioning here. The dimension style I made is annotative. So here's how you're going to do it. We're going to use dim aligned. I showed you earlier an example where dim aligned would not work. Dim aligned will work in this case. And when you do dim aligned, go up to the dimension tool right there. Instead of linear, you can pick it from here or you can type in DAL. Now when you do that, it asks you to pick 2 points, which you can do, but you can also press enter and then you get to select the line itself. So I'm going to press enter. I'm going to take this, snap directly to the midpoint, and you notice it says 110.00 because that's the length of that line. Enter, enter. Do it again. Do it again. Snap someplace on the line, it comes above. Enter, enter. Pick the line, snap there. Enter, enter. Pick the line, snap to it. Enter, enter. Pick the line, snap to it. Now there's all my lengths. However, there is no way. By the way, I came up with this dimensioning system for a friend of mine years ago who was a surveyor who got tired of typing this all in once he'd already laid out the drawing, saying, wait a minute, I already typed that in when I drew it. Why am I typing it in again? There is no dimension tool that will directly put that angle on here. So I'm going to give you a trick, a workaround. I'm going to copy all these dimensions down below each of those lines. I'm going to take each one of them and just put it directly under the bearing. So now obviously that's not the right angle. What it is though is the right location, size, format, and even better, it's still a dimension even though it's not an accurate dimension, which means I can still change what the dimension looks like by modifying the dimension style. So I'm going to pick that. The base point is anywhere. Bring it down below. It looks like that. Now in order, the reason I did that is I want this text font right here. I want to change that from 110 to north 24 degrees 48 minutes 18 seconds west. And the way I'm going to do that is this. I'm going to start with the DI command. Well, it's the dist command, D-I-S-T. I'm going to go to the endpoint. Be careful here. Don't go to the endpoint this way. There are 2 endpoints within that square. You have no idea whether you're getting the endpoint of this line or the endpoint of that line. And I showed you there's a gap there. When you go to the endpoint of a line, don't go right to the endpoint. Go off the endpoint, because until you get to the midpoint, endpoint's going to be picked here, endpoint's going to be picked here. Now if I ask you for a distance, it's going to tell me 110, but it also gives the angle, and because I have surveyor's units set, I get them in surveyor's units. If I highlight that, right click and copy it, now I can double click on this, delete it, paste that in, and then make 1 or 2 modifications. There's some spaces I want to get rid of. The main thing though is I don't want the letter D, I want the diameter symbol. AutoCAD has had some control characters for years. %D becomes the the degree symbol when you come back out. So now I've got north 24 degrees 48. In other words, if I made a mistake when I created it, that number will be wrong. That means I now can look at it and say, oops, I made a mistake. Whereas if I were typing it in, 1, I could make a typo. 2, I could type it in correctly even though when I created it, it was wrong. So this is still a way for you to check your work as you go. And then you go through and you do that all the way around. Say, what's the distance from that point to this point? Now, go up here, highlight it, and you're going to go down on yours. Copy it, double click, delete, paste, get rid of the spaces, just put a %% in front of the letter D, get rid of the other space, click out here, you've got that. Do the same thing with this. Distance comes up here, and you notice it's got to be right. Well, it has to be what you used when you created it. It doesn't have to be right. If you made a mistake there, it wouldn't be correct. Delete that, paste it, come back, do this, %, come back over here, do that, looks like that. So that will give you a way to dimension this. Otherwise, you've got a rectangle to put in, you've got some other dimensions to put in. Those are just architectural dimensions, but not using architectural units. So what you could do on this is you could modify your dimension style so that when you do linear dimensions, you have, let me check one thing. I'm going to pick that dimension. I'm going to look at the properties of that dimension. Yeah, it's an aligned dimension. So what I can do here is this. I'm just checking to make sure this is going to work. If I go back to my dimension style, I can say, all right, that's great, but I also want to have special style for linear dimensions. And the special style for linear dimensions is going to be to go and basically set it up for architectural. So we do want the dimension lines to come in, and we do want the extension lines to come in. Go back to symbols and arrows. Arrowhead size is going to be 0.06, but we're not using actual arrowheads, we're using architectural tick marks. And then under text, we go back to horizontal. Nope. They're still going to be aligned, and they're going to be above. So now, anything else I need to change there? No. So now I'm done with that. Close. That did not work, did it? Huh. Well, the reason I thought it would is because it doesn't call those linear dimensions. So I thought linear. Nope. All right. So those are still seen as linear dimensions. So that is not going to work. So what you need is a whole separate dimension style that is architectural, which you've already created. So bring that in as a second style. That seemed like a good idea, didn't it? At least it did to me. That's it on civil, I believe. Use an architectural title block for civil. Do not use a mechanical title block. Some of you did that for the architectural drawing. Mechanical title blocks have tolerances in thousandths of an inch. Pieces of property do not deal with thousandths of an inch. Sometimes fractions of an inch, but not thousandths of an inch. And then answer these questions, lay it out, put the dimensions on there as shown, and then submit it. You, by the way, are free to do all of these or 2 of these. I'll evaluate whatever you submit and I'll get it back to you.